Hello students, welcome to Inside Physics. Today we are going to discuss about Ampere's circuital law. So this law is about the calculation of magnetic field when there is a current flowing in a conductor or a current flowing across an area of cross section. So this is very similar to Biot-Savart law, but we can consider the Ampere circuital law as a simple method compared to Biot-Savart law. In Biot-Savart law, we already discussed in my previous video the magnetic field around a current carrying conductor depends on three factors: length and the angle between the position vector and the length element vector and the current inside the conductor. Here Ampere's deduced a simple method to calculate the magnetic field around a current carrying element. So we see how it actually proceeds. See, if we consider a current flowing across an area of cross section like this. So the current flowing from left to right we consider as I1, I2, I3. So here the net current flowing through the area of cross section is I1 plus I2 plus I3, which we can say the total current is I. So the current means we know that charge flowing per unit time. So here how to calculate the magnetic field around these three current carrying conductors, and if you consider the total current flowing in one direction as I, and what is the net magnetic field due to the current I. See, the definition says the algebraic sum of the net charges or currents flowing from one direction to other through a unit area of cross section can be considered as the total current flowing in a particular direction. So the algebraic sum means if you are considering the currents from left to right in one direction, and if you say the fourth one may be flowing from right to left, so we can take the algebraic sum of total currents so that we can calculate the magnetic field due to the total current across this area. So that can be considered as I1 plus I2 plus I3 minus I4. So this is the algebraic sum where we consider the sign convention also. These are in one direction and the fourth current is in opposite direction. So how to measure the magnetic field around this current area? Okay. So now according to Ampere's circuital law, we need to have a boundary of around this current carrying elements. So the surface area through which the currents are flowing, the surface area will be perpendicular to this board, or we can consider the surface area is perpendicular to the current direction. So on the surface area we will imagine a boundary. If this is the surface area through which the currents are flowing, we will imagine a circular boundary across the area through which the currents flowing. How to get the idea of that circular area means, if you use the right hand thumb rule, then the currents flowing across this area will be shown by the thumb, and the curl of these fingers will show the boundary that we have taken across this current direction. So you put like this, the thumb shows the current direction and the curl of the fingers in which you are doing the curl like this, you will imagine a boundary across the surface area. So now we say the surface area all the currents are passing through has a boundary that can be written as okay, and we can take the boundary like this. we need to imagine this in a way like this. Okay, so here on the boundary we will calculate the magnetic field. We always know that by Oersted experiment in the beginning of the electricity and magnetism connection where it was found by Oersted, every current carrying conductor produces a magnetic field around it in concentric circles as the current conductor as the from passing from the center through its axis. So here we consider a small element. If you consider the total length of the boundary as L, we consider a small length here as dl. And we know here the magnetic field passing through the boundary, the magnetic effect or the magnetic field across this boundary as per Ampere's circuital law can be written as, see, now what I told you, this dl is a small length considered on the boundary. So the length element will go smaller and smaller. If you consider the length element very small, and the number of length elements will increase, right? So if you sum all the small length elements, it will become an integration. It will become the integral. So if you multiply the magnetic field into small length, and we can do the line integration, which is symbolized like this, and this is a magnetic field vector and the length element vector. Now according to Ampere's circuital law, this is equal to mu naught times the current flowing through the surface. The surface means this is the surface. The surface is like this, perpendicular to this board, and the surface is enclosed by a boundary which we have imagined the boundary, and the boundary has the length, total length. That means if it is a circular boundary, the total length is L, that is equal to 2 pi r, perimeter of the circle. So in that we have taken a small length element, and this element is multiplied by the magnetic field, and while the length element goes smaller and smaller, the number of these lengths will increase, and if you sum all the lengths and the magnetic field multiplied by it, we will get the total magnetic field. So this is the form of the Ampere's circuital law. So if you observe I, what is I? The total algebraic sum of the currents flowing through the surface area in one direction. If you consider from left to right as positive direction, and the negative direction will be from right to left. So this I here in this diagram we can say this is I1 plus I2 plus I3, where we know charge is equal, current is equal to charge flowing per unit time. Okay, if you consider the radius of the circular loop imagined here as small r, that means the total perimeter of the boundary will be 2 pi r. Then this integration will become BL, where L is equal to 2 pi r, the total length of the boundary, and this will be equal to mu naught into IE. This form of circuital law has become after integration like this. So here L is the perimeter, we have integrated these small length elements, and finally we got the total length as L. That length will be 2 pi r, as the radius of the circle or boundary is small r, where IE means current enclosed in the boundary, inside the boundary. We cannot consider any current outside the boundary. We only consider the currents passing through inside the boundary. So IE means here enclosed current in the boundary. Okay, so if you observe, this is looks very simple and lucid when you compare to Biot-Savart law, where in that the magnetic field calculation dependent on 3 factors, and in the beginning also I told you, here it is only dependent on the factor that on the radius of the boundary, where magnetic field can be written as mu naught IE by 2 pi r. So I is the enclosed current, and that will not change until we change the current. The radius, we may take the boundary as our wish. We can change the radius of the boundary. We can select a bigger boundary, or we can select a small boundary regarding the radius. So here it is dependent on the radius. That means from the center of the boundary to the circumference is called radius. So here if you observe this one, we can conclude that the magnetic field is dependent on the radius of the boundary we have taken. So what is the direction of the magnetic field on the boundary? We know that around the conductor the magnetic field will be in concentric circles. In the beginning also we have seen, when we take a conductor, the field will be like this, perpendicular to the conductor, plane of the conductor, and this conductor will be passing through the center of the circle. When these are concentric circles, the magnetic field will be like this around the conductor. So what is the direction of the magnetic field? Means the direction will be quite tangential to the this is the tangent drawn to the field direction. The magnetic field is tangential to the circle, loop. We can say it as circle or loop. It is tangential to the loop. That means, see, we can conclude this and we can implicate 2 points here. The first one is the magnetic field is tangential and it is a non-zero value. It is tangential to the loop and it is a non-zero value. And we can say another thing also, if it is perpendicular to the loop, if it is perpendicular to the loop, that means like this, if the field is like this, and which is not at all correct, we can say if it is perpendicular to the loop, that means it must be having a zero value. That means magnetic field vanishes. It must have zero value. So these conclusions we can draw from this boundary method, where it is easy to calculate in so many processes. Yes, this includes a simple terms like the perimeter of the boundary and the current enclosed inside the conductor. Here the interesting points are, as the magnetic field is tangential to the current, these loops, these loops will be concentric circles, that we can conclude from this. And the magnetic field is having a cylindrical symmetry. What is cylindrical symmetry? If you observe, this is tangential to the loop, and everywhere it is tangential to the loop, the magnetic field everywhere is tangential, means it is having a cylindrical symmetry. Cylindrical means the boundary is like considered as a boundary of the cylinder. So the magnetic field is same at every point on the boundary. That is called cylindrical symmetry. Okay, and the third interesting point is, here if you consider the conductor carrying current as infinite, but the magnetic field is not infinite, it is a finite value. That is the interesting point. So here the finite value is the dependent on the distance that we have taken from the conductor. Here also depends on the point we have taken from the conductor, that depends on the radius of the loop, we can say. So here there are three interesting points. First one, the magnetic field is always in concentric circles around the conductor, and even though the conductor is an infinite conductor, we can have the finite value. And here, see, when we move close to the conductor, when we are moving close to the conductor, the magnetic field will suddenly rise, like it will blow out like to a higher value. So that is the difference when we are really coming close to the conductor. So this is the method to calculate the magnetic field based on Ampere circuital law. On the next video we will see some more topics on moving charges. Okay, if you want to see anything in the form of another video, you can make a comment you want to see, and we will make the video on the based on your comment. Okay.